Hello everyone, and welcome to the One World seminar on Combinatorics onwards. We're very pleased today to have Antoine Julien from way up in the north of Norway. He's going to speak to us about balance in billiard words and cohomology.
Yes, so thank you very much for having me here. It's been a while I've given a math talk, so my apologies in advance if I'm rusty. So I'm going to present a work that we did with Nicolas and Valérie. And so my plan, since I'm not sure that I have full control over how much time it will take, is that let's start with the results immediately, so that if we have a power outage, you still have something to go with. So what we proved in the paper is that sequences arising as coding of billiards in cubes, if the cubes are high dimension enough, and that's that at 3, cannot be balanced on all factors. And more precisely, for cubes of dimension 3, that billiard sequences are not balanced in factors of length 2. Okay, so we need to define a few of these words for these things to make sense. So we need to define billiard sequences and balance. And I wrote subshift here. And so I actually decided not to talk about subshift, even though I may mention them and you may ask me questions about it because they're really behind lots of these things. We need to do a few assumptions, namely that the trajectory of the billiard sequence is irrational. And also maybe something that is kind of the one original point of our paper is that we use some tools from topology and dynamics to tackle these problems. Namely, we use cohomology to talk about it. So part of this talk, so the plan is to define these things, even though I suspect that many of you are very familiar with all of this. So if I bore you to death, my apologies in advance. But then a significant part of the talk would be devoted to try to convince you that there's a link to be made between balance properties on the one hand and cohomology on the other hand. Yes, and also, of course, what cohomology actually is. Okay. So yes, so that's the plan. Define billiard sequences in subshift, define balance, show these results again once they make sense, and then define cohomology for these aperiodic sequences, and then try to convince you that it's a natural object to look at. Okay. Yes. So let's start with a very well-known example. I don't know if that's a mandatory step in any combinatoric of what seminar to talk about the Stoneman sequences, but I took it as such. So I'm going to talk about the Stoneman sequence. So let's say you have a square and you throw a particle, and so this particle bounces on the walls, and you're going to code either by an A or a B, depending on whether it hits respectively a vertical wall or a horizontal wall. So for example, it may start bouncing like so. So the second letter in the word would be B because it hits this wall here. So a usual trick with these billiard sequences is that it's possible to unfold them. So instead of looking at this trajectory that bounces along the wall, you can assume that it just continues straight in a different square. And then it's going to still intersect this. So first it intersects this vertical line, which is coded as an A, and then it intersects this horizontal line, which is coded as a B. So and here again, instead of bouncing like so, you could say that it continues vertically in an once again unfolded billiard on the square above. And every time it intersects a vertical line with integer coordinate, you could with an A. Every time it intersects a horizontal line with integer coordinate, you could as a B. And let's not think about what happens if it hits a corner. Okay, so that's all well and good. But something that you could do as well is to say, well, instead of looking at these things in the plane, we could quotient by Z2, like identify all of these squares as being the same, that instead of having a trajectory in the plane, we have a trajectory in the torus. So instead of the trajectory going here, it would instead go there, like so, right? So you have now a trajectory going in the torus, and you have these two lines in the torus, which end up being two circles. Every time it hits one of them, you code with an A. Every time it hits the other one, you code with a B. So for example, we can look at a few ones. The top interval is identified with the bottom interval in this representation. So it would continue like this. So next one is an A because it hits the vertical one. Next one is again an A because it hits the vertical one, and so forth and so on. So you can look at all these at this whole trajectory in the torus and code code the trajectory symbolically with these infinite words. Nothing prevents you from going infinitely far away in the future or going back infinitely far away in the past. And these sequences are, in my opinion, maybe some of you would disagree, I don't know, but they are mostly interesting, and we're going to be interested in them when the slope is irrational, because then they are non-periodic, and they repeat. So the starting point does not really matter, actually. If the slope is irrational, you have all sorts of nice properties. Okay. Oh, and by the way, I've stated my main result now at the very beginning, so you should feel free to interrupt me whenever you want if you have questions. Yes. Another way to look at these two-domain sequences, and that's a way that I like, it's to look at them as cut and project sequences. So we're going to take a slice of the plane, and so this slice has an irrational slope, which is this alpha here, and so the base of this slice is the unit square, or maybe more generally a unit cube. And we're going to look at which line intervals fall inside the strip. And if we have a horizontal line interval, we're going to code with an A. And if we have a vertical line interval, we're going to code with a B. And you can actually convince yourself that these two are the same, because if you take the trajectory in this example that starts from 0, which lines are being intersected, vertical or horizontal, really corresponds quite well in which line segments are entirely contained within this strip. So if you only keep these points which are inside this strip, and then you project them onto a line, if you like, one-dimensional sequences, let's put everything into one dimension, and then you code with A and B. You have some additional information, which is here the length of the tides, but let's not care about this now. We're just interested in the symbolics of it, the sequence of A's and B's. So this sequence of A's and B's is going to be a Stallman sequence, and that's another way that billiard sequences can be constructed, right? And that's going to be the way. That's going to be the way that we see them how we proved stuff in our paper by looking at these sequences as cut and project sequences. Okay. Yes. So what we are looking at are billiard sequences in higher dimension. So it's still a line which defines trajectory in a d+1 dimensional cube, which we can see by this unfolding trick. Also, that's a trajectory in a d+1 dimensional torus, and we code the trajectory by which of the d faces it meets. And so in a three-dimensional cube, for example, there are A, B, and C. You have 3 pairs of faces, and the numbering of letters which we use to code increases with the dimension. So the cut and project picture of this is that we have a space, a total space, which is Rd+1, in the same way that we had R2 with the Stallman sequences, right? And so we ask, well, which integer points land within a strip which has an irrational slope? This irrational slope is L theta, and the base of this strip is the unit cube, right? So again, let's go back to this picture. We have a unit cube. We push it along an irrational direction to get a tube. And so we ask which of the points fall within this tube. And there's actually a result that you have a broken line of line segments within this tube if the kind of if this tube is defined based on a unique tube. So yes, so you code this broken line of line segment which fall within this tube by letters, and that gives you a billiard sequence. And we're going to assume that the trajectory is irrational, which means that the vector that defines the line has coordinates which are rationally independent. There's a whole lot of result for what it means. For example, it means that these sequences are not periodic. This means also that these sequences are repetitive. Patterns that appear somewhere will repeat infinitely often, and so forth and so on. So I'm not going to talk too much about these aspects. I'm just for now interested in defining what this means. You will also notice that I introduced a point M here. So we look at which points which will fall within the strip. And so instead of looking at the integer lattice like we had here, we could shift this lattice a little bit. And if we shift the lattice a little bit, maybe the sequence that falls within the strip will be slightly different. And what that corresponds to is that we would get a different sequence, but that would be obtained from taking the same direction in the billiard sequence, but a different starting point. Basically, that's what it means, right? So whatever you can do, things that you can say about billiard sequences, there are ways to translate them in terms of cut and project sets. The irrational direction, this L theta, the starting point, this M, and so forth and so on. Okay. Yes. So why is it useful? Billiard or tori are perfectly nice objects. Why would we want to define such a thing? Well, the way why this can be useful, and something that we use in our paper, is that many of the things can be parameterized by this window that is like a cross section of this tube. If you have this tube that you define from your unique tube and you take a cross section, this set you might want to call the window. And so if you have a starting point in this, if you have a starting point for your trajectory in this window, where exactly it lands on in the window will give you some information about what the sequence looks like. For example, you see that if you start if the point M in this half part of the window, then you have room to start with a horizontal vector, like so. So all the points where the starting point of the trajectory is in this part of the window will start with the same letter. Oops. And any point which starts in the other half of the window, you see that you have room for a vector here, but you have no room for a vector there, and which stays in the window. So all the point, if you start your trajectory in this part of the window, then you will start, the word will start with a different letter. Okay, so that's really what we want to exploit, and what we exploited is the relationship between the geometry of the window and the combinatorics of the words. To give an illustration, this is if you have a billiard in the cube, a cross section of the tube can look like this projection of the unit cube, of the three-dimensional unit cube, and there's a partition of this cube where each element of the partition, if you start your trajectory in each of these elements, you can say something about what is the starting factor of your work. And one of the results of the paper, which I stated before and which I will state again, was based on this kind of analysis of the geometry of the window. And if you would indulge me for a minute, that's something that generalizes. I see that Lorenzo and Johannes are here, and looking at the archives of the seminar, I know that they have given talks. So these cut and project sets can generalize to more than one-dimensional sequences. So that's an example. If you have the octagonal tiling, that's a tiling that is created instead of taking a tube, it's taking a slice of a four-dimensional space. the cross-section of this slice is then a two-dimensional window. That's the window. And similarly, as in one dimension, each area of the window corresponds to a certain arrangement of points in the tiling. So here it's not anymore an arrangement of letters or an arrangement of line segments in one dimension, but it's an arrangement of patterns in two dimensions. So just looking at a few examples where a certain part of the window may correspond to different patterns. I find it pretty. So if you, I'm glad that you indulge me these few slides showing the correspondence between window and pattern. Okay. Yes. So now let's talk about balance, because our results are about the balance properties of these words. So the nice thing with these words is that factors in these words have a well-defined frequency under our assumptions, and that means that the balance can be considered as a comparison of the occurrence of the letters compared to the expected frequency. And I will tell more in a minute. But there, you may have met other definitions of balance in the word literature. At least when I prepared the seminar, I saw some other differences, some other definitions. I'm going here to define balance in terms of how things compared to frequency. So if we have a word, an infinite word on a given alphabet, the frequency of a letter is defined as, well, this limit, the number of occurrences of this letter in the first n letters of the word divided by how many letters there were. And then, I mean, maybe you would like to take from minus n to n and divide by 2n plus 1. If the words are repetitive, and if the subshift is uniquely ergodic, it's not really that crucial. So let's put these questions aside for our examples. In our example, it's not going to matter too much. We have some forgiveness in how we define the frequency. But basically, that's what it is. That's the average number of times a certain letter appears in the word. So if you have a frequency of 1/2, it means that on average, half of the letters are A's. So for billiard sequences, these frequency exists, and I said for billiard sequences under these assumptions of irrationality, we do have some forgiveness in how we define the frequency. So I'm just going to leave it this way, where that's on average how many of the letters of these infinite words are A's. One question that you can ask is how fast does it converge? And the balance property that we have is that we can look at the discrepancy between the expected numbers of A within a word of n letters and the actual number of times it occurs. And if this discrepancy is bounded above by a constant, then we say that this word is balanced. Yes. And again, maybe I might be a little bit sloppy in that it should probably independent on which starting point of the trajectory you start with, if you want it to be perfectly rigorous. But that's, I mean, in terms of the idea that I want you to get, and what we worked with is that the balance on word, that's the difference between the actual number of times a letter occurs versus the expected number of times it occurs. And if this quantity is bounded, we say that the word is balanced on this specific letter. If it's balanced, it's balanced on all letters if it is bounded for all letters, as you can expect. It is also possible to define balance properties for finite factors. Instead of looking how many times a certain letter appears, we can look at how many times a certain factor occurs. And if the word is balanced for this factor, if this discrepancy function is bounded, we say that it's balanced. And if the discrepancy function is bounded for all of the factors, then we say that it's balanced for all factors. So basically saying that something is balanced means that these averages converge very well, that the difference between the actual numbers you measure, and the expected number is bounded. Right. Okay, so let's state the results again. If you have a cubic billiard sequence in a cube of dimension at least 3, then it cannot be balanced on all factors. There are necessarily some factors for which it's not balanced, right? So it means that maybe the ergodic averages converge well for letters, say, and actually we'll state that they converge well for letters. If I'm not mistaken, that's a result by Vuillon in 2003. But they cannot be bound, on all factors. There has to be some factors for which it's not balanced. And in dimension 3, we were more precise, and that it's balanced. It's not balanced on factors of length 2. So already for factors of length 2, this balance property fails. Right. Okay. So these are the results, and especially theorem 2 was done by carefully analyzing this sort of figure and the geometry of this partition and what's the worst or best that can happen depending on what the slope is. Okay, so yes. Are there any questions so far? Okay, so yes. So as I said, the results that I stated now, they really rely on relating, on the one hand, balance properties of these billiard sequences and cohomology. So I'm going to define cohomology, and I'm going to try to convince you that it's related. And I don't know how much I'll be able to say in terms of how we proved it. But basically, this link between balance and cohomology is really the crucial one, because then it means that we can invoke other results from the literature, namely some result by Johannes and Lorenzo. Okay. So yeah, what's cohomology? How are they related, and why does it help? Okay, so I decided for this one, and there are many, many ways to define cohomology. There's an expression in Norwegian, I don't know if it's also in other languages, as two people get three answers, and when it comes to tilings, that's especially true. But let's start with the definition of cohomology that you may have seen in algebraic topology class. So we start with a cell complex. So in one dimension, that would be a graph. It's made of vertices, points, and edges, intervals. And we're going to assume that they are oriented. And so there's a boundary function. So if you have an edge, there's an endpoint, V1, and there's a start point, V0. You could write symbolically that the boundary of an edge is V1 minus V0. That's a purely symbolic notation. That's a symbolic subtraction. If I want to define a cocycle that's a function defined on the edges with value in a certain ring, people typically choose Z or Q. In this case, we're going to choose R, real valued. And a cocycle, it's there's a pairing between cocycle and path of successive edges. If you have a path of edges which are all one after another, the cocycle pairs with the path by just taking the sum of the values on each edge. So the cocycle can give a value on each edge, but it means also that it can give a value on each path, right? And we say that a cocycle is a coboundary if, and here maybe I loaned some language from physics, maybe, if it derives from a potential. So if there exists a potential function defined on the vertices, such that the cocycle on each edge is just the difference of potential. So for example, in an electric circuit, voltage is a coboundary because it derives from a potential, the electric potential, right? And so when you have a coboundary, you can check that the value, the sum of a cocycle along a path and the sum of the same cocycle along a different path only depend on the start point and end point, because that's the difference of potential between these points. Right. If you have a cocycle which is not a coboundary, then maybe the evaluation of this cocycle along two different paths might be different, even though they start and end at the same points. So that's kind of the idea. And the cohomology is it's then the quotient of all cocycle quotiented by all coboundaries. So that's a quotient group. And generally speaking, in graphs, cohomology, the dimension of the cohomology counts how many loops you have, how many different paths you have in order to get from point A to point B. If you have several loops, then maybe you have several different choices to get from point A to point B, and that will allow you to have several cocycles which are not equivalent to each other. Okay, but let's take a very silly example. Let's take the real line, which I'm going to decompose as a graph by taking points, for example, the integers, and then taking edges, for example, each intervals. And in this case, you would say, well, but wait a minute. If you have, let's say I have a cocycle, so I take some values, for example, 1, 2, 1, minus 3, and so forth and so on. Any cocycle derives from a potential, because I could choose a potential which is, for example, 0 here, and then the potential is going to be 2 here, and 2 plus 1, 3. So by just summing the cocycle, I just have one path from any one point to another. So any cocycle derives from a potential. And if you remember, or if you've taken algebraic topology, maybe you would have a more sophisticated argument of saying, well, but the real line is contractible, so the cohomology is trivial, and so of course all cocycles are coboundaries. And that's true. That is true. In this case, cocycles are the same as coboundaries, and so this group, this quotient group, which is the quotient, is trivial, right? Now, let's do a slightly less silly example, and an example that is related to an award. So let's label each of these edges by letters of award. So take your favorite infinite word, for example, a Stormian sequence, and then take the same graph decomposition, but add the additional constraint on cocycles that they need to have the same values if you have the same letter. Okay, that's a fairly stringent condition. So maybe you want to say that the value along an edge, the value along an edge xi, only depends on a finite number of future and past coordinates. For example, you could have a coboundary which is 1 whenever you see BAA, but is 0 otherwise. So here it's BAA, so it would be 1. Here it's AAB, so it would be 0. Here there's a B in the middle, so no discussion, it would be 0, and so forth and so on. So you could define co-boundary like this, which are related to your word, where you have a combinatoric restriction on which values you're allowed to have. And this restriction is that the value on the edges only depends on a finite number of past and future coordinates. Right. And similarly, the acceptable coboundaries that may give a restriction on your potential that your functions are allowed to derive from. So maybe you have a function defined on the vertices that where the value on one given vertex has to only depend on a finite number of future and past coordinates. Notice that I said finite, I didn't say bounded. So that means that a certain cocycle may very well depend on only the letter. For example, you could have a cocycle which is 1 whenever your edge is an A and 0 otherwise, or you could have a cocycle which is 1 whenever your edge is AAB and 0 otherwise, and so forth and so on. So two different cocycles don't need to depend on the same number of coordinates. Right? So now things become less trivial. You have fewer allowed cocycles because you have this constraint that values on the edges have to repeat whenever the the words repeat, but also you have fewer co-boundaries because the same constraints applies to the potential. And so the result that we get is what we call pattern equivalent cohomology, which also happens to be the Chesh cohomology of the subshift. And I didn't say what the subshift is, but that's actually only depends on the specific subshift. So if you took a Sturmian sequence in this example, it would not, the cohomology group that you would get would not depend on the specific sequence, but it would depend on the subshift that the sequence is in, right? And we're also going to create strong cohomology for a reason that will become apparent a little bit later. So now these groups are typically not trivial. They are, as I said, this example of the real line is trivial. This example suddenly is not. And if I'm going to do a quick side comment here, that you're welcome to look past once we come back to the main stream of the presentation. But generally speaking, when talk about cohomology for subshifts, there can be two pictures of cohomology. One of them is looking at what happens on the subshift, kind of a transversal view. And one of them can be to look, if you see your subshift as a Z dynamical system, to look at what happens on the orbits. And so this, the way that I presented it here, is kind of an orbit view of this cohomology. There's a corresponding kind of transversal view or subshift view of this cohomology. So there are usually, it very well may be not the first seminar about cohomology that you attend, and it may very well not be the same definition. As I said, that's as two people get three definitions for cohomology. But generally speaking, they fall into two sorts of categories, either the orbit view of the cohomology or the subshift view of the cohomology, longitudinal or transversal. Okay. Yes. Okay, so I want to illustrate what cohomology can be used for, and I'm going to take a slightly older example. When I prepared it, I was about to say, I wrote an old example, and I thought maybe I should be careful because some people will have been born at these dates. But anyway, let's still create a less recent example. If you have such a cocycle which have positive values, maybe you can want to say that you want to make your subshift to a physical tiling where the length of the tiles is given by the values of your subshift. So for example, you have a cocycle which has value 1 on A tiles and value 2 on B tiles. Well, suddenly you have a tiling where the B tiles are twice as long as the A tile. So if you have such a cocycle as we defined earlier, then you can use it to define the length of a tile and turn your combinatorial word into a physical tiling of the real line. Maybe it's a little bit of a stretch to create a tiling, but at least you transform a Z action into an R action by continuous translation. And this was actually used by Parry and Sullivan and Parry and Tunstall to study flow equivalence of subshifts. So if you have a subshift, you can define a length function and define the suspension of the subshift. And so you can ask, when is it that two subshifts are flow equivalent? And what's underlying in these works is the first cohomology group. If you have a function that defines the length of the suspension, then it defines a certain class in the first cohomology group. Okay, but for us, we're going to use it differently. We're going to use it to try to talk about balance. So how does cohomology help studying balance properties? Okay, so the key point is that letter counting functions are cocycles. And to give you an example, let's say I want to count how many ABs, I mean letter counting functions or pattern counting functions. In this example that I wrote the cocycle that counts the occurrences of the factor AB. So whenever you have an AB that starts, mark the first edge with a 1, And same thing here, because you have an AB, and then you would continue for your whole word. So this is a cocycle because it only depends on finitely many coordinates. So here it just depends on the current coordinate plus one in the future. And so, yeah, so basically that's the key observation, that letter counting functions or pattern counting functions are cocycles. Okay. And so what does it mean then in terms of cocycles to say that a word is balanced on the factor AB? Well, it means that if you take the first n subfactors and you count how many ABs there are, then and you take the difference with the expected number of values, then it has to be bounded. It has to be less than C. And here I wrote it using this indicator function. What it means is that if you just take the cocycle that is one on every single edge, then that's a cocycle. It's just one everywhere. That's the unit cocycle that counts the number of letters. So you can write this discrepancy function, actual number of occurrences of a factor minus expected number of occurrences. You can write it as a difference of cocycles. And so it means that it's an element in the cohomology. Well, the question is, when is this difference bounded? And there's a result by Gottschalk-Helden that says that this difference is bounded if it derives from a potential. In other words, this difference is bounded if it's a coboundary. Now, there's maybe a little kind of fine print in the bottom of this statement, is that the coboundary that it will, the potential that it will derive from, or in other words, the function that it will be a coboundary of, it will not depend on just a finite number of future and past coordinates, but it will be approximated by such a coboundary. So we call it a weak coboundary. If you like to think about subshift, that's the same difference as locally constant functions on the subshift. That's kind of a strong condition. It depends on finitely number of past and future coordinates versus continuous function on the subshift. Then you have something that's just approximated by locally constant functions. Right. So yeah, so in other words, this discrepancy function is bounded if the difference of this cocycle minus this cocycle is a weak coboundary. So we have a cohomological condition in order to say, well, yes, this is balanced, or no, this is not balanced. It's, well, does this class belong to this subspace, or does it not belong to this subspace? Yes. So where do we go from them? Yeah. So let's try to illustrate what these cocycles are. So we know that Sturmian sequences are balanced on letters. So that means that if you take the A counting function and you subtract the expected values of A times the number of letters, then it has to be bounded. And it derives from a potential. It derives from it's a coboundary. So what is this B? What is this potential function? Now let's have a look at this thing here. Let's look at the word that starts here, and that's a broken line from all the way to here. So it's going to be A, B, A, B, A, A, B. Okay. Well, because I started at this point and I ended at that point, I know that the B's are overrepresented compared to the expected value. And the reason is because when I project this point, the endpoint, back into the window, well, this displacement here is in the B direction. As opposed, I mean, to take another example where the A's are overrepresented, let's just take the one letter word, which is just an A. Well, the start point is here and the endpoint projecting the windows there. So now the displacement is like so, And that means that the A's are overrepresented, which is expected. If 100% of your one-letter word is an A, then certainly your A is overrepresented. But the punchline is that by looking at the relative position of your endpoint and start point projected in the window, you can say if the A's are being overrepresented or if the B's are being overrepresented. And one way to define this potential function, well, I'm probably going to define a multiple of it, but up to scaling. One way to define this potential function, let me just clean up this a little bit. Yes, so take a function that is 0 at the origin and that just measure your perpendicular space. So 0 here, 1 here, and linear otherwise. Now, the value of a point B of a vertex is, well, take this vertex, project it. What's the value? What does it fall? It's positive on this side. It's negative on this. It's negative on this side. So this side is negative. This side is positive, right? So that's a function that is going to be the potential function that makes this discrepancy a coboundary. That's one way to see that Stallman sequences are balanced on letters, that you can define such a function. You can define such a potential function on the window that tells you whether A's or B's are overrepresented. And now it's pretty clear that it's bounded because no matter what my start point is and no matter what my end point here is, both of them are going to project within the window, which is bounded. So the allowed values for B of a vertex are going to be bounded above and below. So these differences, of course, going to be bounded. So yeah, that's one. That's the cohomological picture of saying that Stallman sequences are balanced on letters. Yes. Okay, so now the dimension. Now, since we talk about cohomology, let's try to give an example of a cohomological argument. The dimension of the first cohomology group for Stallman sequences. Oops, sorry about this. That's a capital S. Is 2, and that's something that you can compute. We're not going to do it here. I'm asking you to believe me. So the dimension of H1 is 2, and it's generated by the A counting function phi A. I mean, okay, so you can find several generators. I should have taken another one for the first one. It's generated by the letter counting function, this that I wrote, the indicator function, and the discrepancy function phi A minus 1. You could say it's generated by phi A and phi B, the A counting function and the B counting function. Yeah. Sorry, I should have the discrepancy function needs to take into account the measure of A. But any two reasonable generators you take will do. So it's generated by the letter counting function and it's generated by the discrepancy function. And so since it's of dimension 2, it means that any other factor discrepancy function is going to be a combination of these two up to a coboundary. So, but coboundaries are not dangerous when it comes to looking at this discrepancy. So it means that Stallman sequences are going to be balanced on all factors, right? So billiards in the square, that's balanced on all factors. Billiards in the cube, not so much. For higher dimensional billiards, and here I'm going to go maybe a little bit fast, but my main point that I would like you to take home is that really this relationship between cohomology and balance. But the arguments that we used in the article is that if you have higher dimensional billiards, then this cohomology group is still generated by the factor counting functions, but the dimension is infinite. But by opposition, the subspace of H1 of these things which are weak coboundaries is going to be a finite dimension. So what it means is that it's not possible for all discrepancy functions to be balanced, to be coboundaries. There are too many independent discrepancy functions, and the subspace of these discrepancy functions which are going to be bounded is too small. So that means that it's not possible for billiard sequences to be balanced on all factors. And so that's kind of the gist of the argument. Um, but yeah, so this translating to the cohomological formalism really allows to take some previous results. Yeah. And so I almost want to stop here, actually. Maybe I should ask and take some questions, if that's okay.
Thanks, Antoine. Yeah, does anyone have any questions? Hajime.
So thank you for that talk. I have a question about this page. So this page means that this not all of discrepancy functions can be bounded. I'm interested in the upper bound for discrepancy functions.
Oh, yeah. I mean, we take an absolute value, right?
Yeah,
So,
absolute bound. No. So it's not bounded, but is it possible to consider upper bounds or something?
oh, you mean like
Yeah.
is it dominated by? Can we find that it's dominated by certain functions? Is it what you're asking, or?
C and instead of C, absolute value C.
No, it cannot be bounded by. I mean, some of them cannot be bounded by any constants.
No, C function C n. C depends on n.
I do not know. I don't think we have results about this. Okay, so um, that may tangentially be related to your question. We have some result with me and Alan Haynes and Jamie Walton and Henake Vissalo. We had some result on the discrepancy functions, on some bounds for the discrepancy functions for cut and project tilings which have a that are valid for almost all slopes. So that's kind of statistical properties of typical cut and project sets, maybe something like that. But I would need to look into it to see if our results are exactly related to these kind of things. Yes. But yeah, if you want to have domination by functions, yeah, maybe you could have a look at the paper that we had with Jamie Walton, Henna Koivusalu, and Alan Haynes on statistical property of typical cotton projects.
Thank you.
You're welcome.
Lorenzo.
Yeah. What we've got is in this situation, you've shown us that the counting functions for the letters,
Yes.
are as constant plus asymptotically negligible, but the counting functions for more complicated patterns aren't. And that
Yes.
means
So
that if you
what you
do a
have in
shape
your
change,
article,
if you do a shape change according to just the letters, you introduce a time delay for bouncing off of a wall, it doesn't really change the dynamics. But if you do a shape change based on a 2-letter word or a 3-letter word, then that should change the dynamics. And I think that it would be an interesting problem to consider some of these shape changes to billiards based on the longer words, and that'll give you a different dynamical system, and it might have interesting properties.
so that's what you called slip and non-slip deformation. Am I correct?
I don't know. I don't use those terms.
I know that these terms appear in some articles which have your name on it, but with Lorenzo, with Johannes, so maybe we can blame him.
Yeah, I think that was a paper where I wanted a bunch of terms that came from Jabberwocky that certain things were brillig or slithy, and we changed them to other terms. No, but just in general, you have the property that if you have a Sturmian sequence and you just vary the lengths of the tiles, it doesn't do anything. It gives you the same dynamical system up to an overall scale.
Mhm.
And what you've shown is that if you do this in higher dimensions, that the changing things based only on the lengths of the uncolored tiles doesn't do anything. But if you change lengths based on colored tiles, which is based on the appearance of sequences of length 2 or longer, then it does change things. And it
Yeah,
would
I
be
mean,
an interesting problem to investigate. How does it change things? How does it change the dynamics?
and I mean, what I explained for Sturmian sequences, and that that generalizes, and that's also an observation I think in your papers, that some classes of which are weak co-boundaries, you can really show them explicitly, and these are these letter discrepancy functions. If you have a point that starts here, like if you have one of these broken lines in the three-dimensional billiard, so you have to imagine that they come out of your screen, and the starting point of the trajectory is here, and the end point of the trajectory is here, then it might mean, by just looking at how it differs according to a certain direction, it might mean that one of the letters is overrepresented or underrepresented. And so these classes, these overrepresentation classes of letters, these are weak cohomology classes. And what you proved with Johannes is that these are the only ones.
Right. Right.
You
So if you
showed that
look at
that's the dimension of the
based
thing.
on two-letter words, you really are changing the dynamical system.
But are you sure that it's automatically on any two-letter words?
No,
Or could you
no,
have
but there
some
exists some
coincidences?
two-letter
Okay.
words that
Okay.
would change the dynamical system. So what you were looking at is at the counting aspect, which absolutely correct. This is a nice result. But I think that would be an interesting further direction to look at the dynamical aspect, to say, okay, here we have something whose discrepancy is not bounded. Do a shape change based on that, based on the occurrence of, based on the discrepancy of that thing. That gives you a different dynamical system. What are the dynamical properties of that other system? For example, is it still cut and project? I don't know whether it would be or wouldn't be. So I think there are some interesting questions that you could approach from this general setup. I'll shut up now.
Johannes, did you have a question?
Yeah, I have a question. Just you said you have some more specific information if the dimension is 3, namely you could show that the two-letter words already are not balanced.
Yes, and here I'm really hoping that Nicholas is in the room. But yes, three-dimensional billiard sequences are not balanced on words, and it's looking at these. Well, the question is, can you have coincidences where these lines that define the partition for two letters may, intersect or overlap in some ways that make balance happen for no good reason?
Okay.
So that's really looking at the properties of, I mean, at the slope basically. So that's a little bit more specific than just looking at cohomology from a distance.
Or maybe I just can add, so instead of Nicolas, I just can say that we look at the shape of these cells, and there are some restrictions on the shapes that give bounded reminder sets, which is equivalent to balance. So it's really looking at the geometry of these cells that we can disprove balanceness, even if their measure is related to the frequencies of the rotation, which is of the vector which is behind. So it's not only a question of measure of the cells, which is necessary condition, but the geometry itself, by using results on bounded reminder sets for total rotations, allows us to say that we can't have balance.
And what kind of geometrical property would that be?
It's that we have so criterion saying that you want the vertices of the cell BB, for instance. We want all the vertices to belong to Z alpha Z plus Z, or and this kind of properties.
I think that the second property is that, so for example, in the picture of Antoine, you see BA. So it is a quadrilateral, and in fact, it must have a parallel opposite side of the same length. And in this case, it is not, the other two are not parallel. It is,
Okay.
yeah, I think it is something like this. And as say Valérie, when you have the vector of the billiard trajectory, you can compute the area of each polygon here. And so this area must have some algebraic properties, and moreover, the polygon must have some geometry properties, which is something like, I think it must have parallel opposite faces, if I remember correctly.
So what Valerie said sounds a bit like rank of stabilizers of these lines, right?
Not sure.
Yes, in some yes, in some yes. No. Yeah.
Okay.
I will say maybe, because I note that the stabilizer has parallel to the edges of the big hexagon, if I remember correctly, but after. Okay, so yeah, I will stay with maybe.
Okay.
Can it be a little bit more than the rank of the stabilizers if it has to do on the endpoints as well? Because the endpoints have to be in
it was
certain
the first
specific
condition
subgroups.
said by Valérie on the vertices, but be in the lattice defined by.
Okay. Well, thank you anyway. It's quite interesting.
Are there any other questions? Okay, if not, thank you again, Antoine.